Hello, everybody. Thanks a lot for logging in on this virtual series of presentation of the EGP program. And thanks, Jill, for this really nice introduction. So like Jill said, I'm not going to present any result today, but really just like what we're actually aiming to do for this new project hosted under the environmental geoscience umbrella. So basically what we want to do is to develop a new kind of geochemical tool that will help to improve the characterization of paleofluid in sedimentary rocks. So the title is a bit different from before, but this is what we want to do. And this will help in assessing the stability of deep geological repository for nuclear waste. So this project is in collaboration with the University of Ottawa and also with Nuclear Waste Management Organization that is funding it. And we have a new PRP that will work on this project, Benjamin Fosiu. So we'll develop this automatized clumped isotope measurements method on dolomite, and then we will calibrate it, and then we will apply it on some sites that have been that are investigated by a Nuclear Waste Management Organization as potential site for deep geological repository. So a little bit of context here. I'm going to try to put my pointer. There you go. Here we see the Michigan sedimentary basin. One of the sites that is currently investigated as a potential site for deep geological repository of nuclear waste is sitting somewhere here on the eastern flank of this Michigan basin. It's really like the idea is to use a deep geological repository as some sort of a multi-barrier system for radionuclides. And really the idea is to take advantage of the long-term stability characteristic of the geological realm. But of course, you really need to assess carefully the stability before putting any nuclear waste down there, because you're gonna have some legacy after that. So we will be looking after the geochemical tool is developed. We'll be looking at some sedimentary rock from this part of the stratigraphy, which is basically the Paleozoic succession going down to the Precambrian basement. So some of the data that has been produced here are the one on hydraulic conductivity. You can see here that we have very low hydraulic conductivity in the Ordovician shales and limestones. We're looking at something down to 10 to the minus 16 to 10 to the minus 14 meter per second, which is one of the lowest reported in the world for this type of sedimentary rock. So that's a very interesting site to confine wastes that are dangerous on a very long time scale. Really, I will not show you a lot of geochemical data, but just a little bit, just to give you a hint on what helped us to describe the sedimentary package as mainly two systems. One that is extremely tight and confined for at least 260 million years, and that would be this part of the stratigraphy here, where some clumped isotope on methane have been done. And also isotope of helium that allow to date the actual confinement of the system. And the isotope, the clumped isotope on methane allowed us to show that the methane was produced in situ in this part at very, very low rate and at very low temperature. What is interesting is the lower system right down there, where you will have a clumped isotope temperature of methane that goes up to 120 degrees Celsius, which is clearly really higher than the paleogeothermal gradient at the maximum peak burial, so the maximum temperature just due to burial. So this methane, that allowed us to tell that this methane was probably from an alloctonous origin and coming maybe from further afield in the basin. So that is a hint toward a lower system that is actually probably more complex in terms of paleofluid history than this confined system just above. Previous work before those clumped on methane were done by Petz et al. in 2017, and they looked actually at the lower part of the stratigraphy, so more the limestone that are just overlying the Cambrian and Precambrian basement. And they looked at different carbonate phase in the limestone, so as well as the matrix, but also like secondary carbonate, essentially, so vein and vugs, and looked at fluid inclusion in there. And they were able to define quite a bit of different stages with different like fluid event and with different temperatures. Some of them were going up to 120 degrees Celsius, but with very small feature, very small vein, etc. So question remains, like we can see here that there is a lower system with very complex paleofluid history, but an upper system that is really tight and confined for a long time. But when we see this type of complex history, there are questions that remains in terms of how, if we don't see really evidence of large-scale fluid ingress in that, what possible effect could we have had on the rock from the heating event that we're still recording in the fluid inclusion? So this is where we want to apply a new type of geothermometer that we've been developing for the past 5 years now, I think at the GSC almost, maybe a bit more. And this is the isotopic clumping on carbonates. So the idea was that we're using like a mass spectrometer, the MAT253 Plus, that is really sensitive, and an automated preparative device for the carbonate. The idea for the geothermometer based on carbonate, on clumped isotope of carbonate, is that the lower the temperature of the fluid where you will precipitate your crystal of carbonate, the more of bond between heavy isotopes, C13 and O18, you will find in the mineral lattice. The higher the temperature of the fluid in which the carbonate precipitate, the less bond between C13 and O18 you will measure in the crystal lattice. So basically, if you're able to calibrate that to measure the amount of bond in carbonate that are of known temperature, you end up with a single-phase geothermometer. So we have done that for Calcite at the Delta Lab in Quebec, at the GSC, and we produced nice hydrothermal synthetic calcite in this type of high-pressure, high-temperature apparatus, and calibrated it between 250 and 5 degrees Celsius. I'm actually lying, went up to 726 degrees Celsius to 5 degrees Celsius. And we're really comparable and indistinguishable to other laboratories in the world that are doing that. So we want now to pursue that to dolomite and produce some synthetic dolomite and then calibrate it after having upgraded properly the system. And then the application of that is to measure this clumped isotope indices on colocalized dolomite and calcite phases to provide, of course, additional information on the temperature history of the sedimentary package, have like more information on temperature when you don't have fluid inclusions, but also further investigate the possible extent of suggested conductive heating on the sedimentary rocks in southern Ontario. So for example, you got a hot fluid coming into a vein that it obviously heated a bit like the rock around it, the matrix, and did that modify the actual isotopic clumping of this matrix around. So with that, I will just like to acknowledge Nuclear Waste Management Organization for their help setting up this project and for funding, and especially Laura Canal-Morrison. And I think I'm done.